Okay, and we're off. Thanks everyone for coming. Today we have Theresa Eimer joining us today from Leibniz University of Hannover, where she's working on her PhD, focusing on dynamically adapting RL agent behavior with her supervisor, Marius Lindauer. Theresa is going to be sharing some of her work today with us on using AutoRL methods to help make RL more robust and reliable without the need for extensive hyperparameter tuning, something that I think we'd all be very interested in knowing more and having access to. So with that, I will hand it over to Theresa.
Wonderful. Thanks for having me. Yeah, I want to talk a bit about AutoRL, specifically starting at the hyperparameter level, because I think that's both super interesting and important, but also where I hope we can use the hyperparameter level to get towards this, somewhat self-tuning RL paradigm. So let's get started. Okay, as we kind of all know, this is reinforcement learning is a bit special compared to many other AutoML paradigms because we kind of have the data collection and the model learning intertwined. So we don't just have some data, train on it, have a model. We have some data, we train on it, and we use the model to generate more data. And that means we have a bunch of design decisions everywhere here. We have things like reward shaping or task generation, task ordering on the side of the data generation. That's really important to get a better model. But also we have things that are in between, like exploration. We have different algorithm choices, even though we've seen things like PPO being quite dominant. There's still different algorithms that work best for different domains. And then we have the typical optimization hyperparameters flying around. So there's a lot going on that in principle needs some sort of configuration, needs some sort of choice. And that's a part what makes this idea of having an automated reinforcement learning process where you really don't just need to push a button, say, I want a solution for the tasks, right? That just makes it very hard. But I mean, there's people working on this, and there's a formal definition of what AutoRL actually means and how we can, deal with all of these different things. And that kind of assumes that we see the reinforcement learning problem as maximizing cumulative reward. So wonderful. The animation does not do what I want. Okay. Basically, it says we say reinforcement learning is this function where we want to find policy parameters that maximize an expected reward, and this function has some sort of training configuration. And the training configuration in this case is comprised of all the things I just talked about on the last slide. Things like the algorithm. How do we actually get our data? How do we optimize a policy? And this is very interesting. And then an AutoRL on top of that is a different function, function f, that really is looking for this training configuration, such that we get a reinforcement learning process that can do its job really well. Sorry for whatever I did with these animations here. So we can see it as an outer loop function. Doesn't mean that really only happens in the outer loop once, can interact with this training process in different ways. But conceptually, when we talk about AutoRL, we usually talk about something that is on top of the process that tries to do something with it. That can take many different forms and has, many different reasons for being challenging. One thing is, of course, that whenever we need to touch this process, several components need to work together. So, for example, if we touch the exploration, we still need to make sure that the model learning actually works well and that whatever task we explore actually fits to what we want to do. Then obviously we might need different data during training. So we know that in, for example, epsilon, typically we want a decay in there because we want a different kind of data distribution as our model gets better. And that is also true for more advanced things, like, for example, curriculum learning really shows that having different data, better suited data to the agent, especially in the end, is important. Then we also need to fit that data in some way. We need to deal with the instability that comes with. And then even the issue is that we know that for all of this, hyperparameters, like really small things like learning rates, really then suddenly have very different values, depending on which point in the learning curve we are, all of which is very, very annoying. And we've seen that to counteract that, we can do some meta-learning of components. And sometimes that's even important, right? if we think about successful applications of intrinsic rewards, or as I mentioned, curriculum learning has moved a lot towards good task generation in a while. Yeah, so there are options to tackle it. And I think meta-learning, as I said, is a really good one. So we've seen that we can meta-learn algorithms completely. There's a few new works on this actually, where we just learn the whole algorithm, don't deal with any of these annoying small componentry, any of the hyperparameters anymore. Or we just learn a reward function, which helps us get rid of a lot of this exploration mechanism, or at least of the configurability of this exploration mechanism. Or we even look at stuff like action options, which again makes this whole process of the data generation and the learning as a composite just easier to conceptualize for humans. I think that's one of the big benefits of meta-learning, these big things that we have to configure this, right? We just have to invest the compute up front and manage to do it correctly. Another successful example is curriculum learning environment design, where again, we kind of try to do these things at once, so exploration and the data generation, so that we ourselves have to do less. Some intelligent exploration, but what I really want to talk about is the thing where we haven't done it very well yet. That's hyperparameter optimization. And I think a big reason why we haven't done it there yet is that, as I said, a lot of these bigger concepts, they really try to eliminate hyperparameters in a way, eliminate the need to touch these many things. And if we actually want to optimize a hyperparameter or automate a hyperparameter, we still need to take care of the rest of it. So even if we say we focus on something that's typically important, like a learning rate, we still have to figure out all the data generation pipeline, which it's harder to get started in, I think. But I think it's very important. And I think doing meta-learning hyperparameter optimization well is a great gateway into doing AutoRL well consistently. And I'm going to get into why. So first, why is HBO in itself important? And I think you already know this if you've used RL for any amount of time. And one of the crucial points here, I think, is that the policy updates we see in the moment actually influence what happens in the future, influence the data we see in the future. So if we make bad decisions in policy updates or have bad configuration for the policy updates, an extremely high learning rate, for example, and then our policy goes off the rails, then our future data distribution will suffer. That's very bad for learning. That's something that's also, in a way, a bit unique to reinforcement learning. You can still, of course, with something like a high learning rate, really set your learning process back by a lot in supervised learning, but at least your data will stay the same. You won't degrade your data quality usually. This is what can happen easily here. So the risk is a bit higher in bad configuration, and we need to be more dynamic. We also know that RL algorithms are sensitive to the hyperparameters. They're not just sensitive to 2 or 3 hyperparameters, they're sensitive to a lot of them. We've actually shown this. This is some results from ICML paper we published last year. We tried 128 settings in total. So it was 3 algorithms and all of the hyperparameters that were exposed in the stable baselines implementation of them, and quite a few environments each. So SAC, TQ, and PPO, I think. And all of those 128, we only saw 8 combinations of algorithm, environment, and hyperparameter, where the worst value is within the standard deviation of the best value, meaning that it's kind of not very relevant to do it well. What we saw more often is things like this, where the number of epochs for PPO and Acrobat is actually, in my opinion, more important than I would have guessed. And we can observe the same thing on things like mini-grid, where, for example, the batch size really surprised us, that the batch size is such an important hyperparameter here, which, of course, we've then seen confirmed. I think there was a paper on last NeurIPS that studied the batch size here as a hyperparameter a bit more. So that's really important, right? So we have hyperparameters that our algorithms are sensitive to, but also they're sensitive to most of them in some setting. That's bad for touching them manually. That's really a good argument for doing it automatically. because if you try to set, I don't know how many hyperparameters is standard PPO, for example, has, but I think we used 11 or something. If you try to really set 11 or just 8 of them well for a given setting that maybe you're even new to, you're going to run into a lot of issues. So you really have to trust that at least some of those defaults work for that, whatever you want to do, which in turn kind of constrains really where you can use your algorithms. And what would also
I guess quite a quick question. Over the course of this work, do you see any commonalities of hyperparameters that are important, or behaviors or specific setups that you see common hyperparameters that are important that are shown through the AutoRL methods? Or maybe I'm skipping ahead.
No, but I was, well, it's always very hard to judge, I think. So what we definitely see is that there are large differences. Definitely, that this is actually my next slide, that the hyperparameter importance is really different depending on the domain we're looking at, which is for the same algorithm in this case. We see that really probably it would be enough if we looked at someone of like the 2 or 3 most important hyperparameters, but they change significantly. And that's also something we've seen in the effect size. So even if a hyperparameter is important in the sense that an algorithm is sensitive to it, yeah, sometimes it's the difference between mediocre and very good. Sometimes it's the difference between, there's one single value where I succeed and the rest I fail. But that's, from looking at it, I couldn't really extract any commonalities that told me, yeah, that's exactly, an overarching pattern. On the other hand, we try to focus on covering a wider range of domains without going too deep into comparison between similar domains. For example, we did 3 robotics environments, 2 like these grid exploration environments, and then we did some of these, smaller physics simulation gymnasium style things. And I would say that's a really small sample of each domain. So, just because for example, the Walker environments. We looked at 3 robotics Walker environments, and they had a relatively similar behavior when it comes to the clipping factor of PPO. So the clipping factor was, the best values were really, really high, which we didn't expect. That didn't translate to other domains. But I would also assume that, this might be a bigger factor, a more interesting question to ask if we compared not against the mini grid thing, but against another robotic simulation that maybe doesn't target walking. That's maybe more like an RM thing. And we just didn't explore that yet. Unfortunately, there's not a lot of data on this out there yet. Yeah.
Awesome. Thank you.
Yeah, I'd be very interested in this too, because I feel like there should be more of a sliding factor. And I think anecdotally there is, right? I think for you that work with reinforcement learning a lot, usually if you see a new environment that has similarities to something you've known, there are some settings that you probably intuitively feel like should work better. Like if I see an environment, I have an intuition of, I'd probably rather use something value-based, or I'd throw PPO on this in a way. But I don't think we really have the empirical data of it yet. I'm not really aware of studies like we've done last year before, because it's expensive. It's really expensive to run. So this was more like focused on the breadth, but I am actually interested in seeing like the details of it as well, and hoping that we can find more commonalities that way. But anyway, yeah, this is basically kind of what I wanted to say here, that we find these really interesting discrepancies of these 4 most important hyperparameters that are quite also, that they have a nicely similar probability, as in, this is like the probability, that's how much they contribute to the total importance. That's quite high, and it's quite distributed over these 4 hyperparameters that really don't matter a lot on a different environment for the same algorithm. And yeah, it's also the other way around, where again we see a mini grid, this batch size, it's hugely important, but that's really not that much of a factor. So if we get it wrong, we can probably mess up our Acrobot performance. That's what the sensitivity part means. But if we get it right, it's also not the deciding factor. The deciding factor will probably be more, do we set our gradient steps correctly? Also, another hyperparameter I was interested to see there, because yeah, that was something I didn't expect, and something we also didn't see for the other domains. So I'm looking forward to someone figuring out how we can actually compare domains here. Yeah, but what we've also found looking at the literature is that if we try to apply an algorithm to a new domain, often you do need hyperparameter optimization of some sort. And for that, what's common is actually grid search. And we found some very large grid searches in the literature, which, I mean, large to a degree where I personally, in an academic setting, would probably not want to run them, maybe even can't. There are methods that are specifically tailored to hyperparameter optimization in reinforcement learning, though. There are quite a few of them, and I think the first one that specifically targeted RL might have been the population-based training paper, the original one. I think that's the first one that was really saying, okay, we focus on RL. But I think it's fair to say that there's no established user base here. You see some of them mentioned sometimes, not very often. I'm going to talk about why in 2 slides. And there's also no like established testing grounds for them. If you look through those papers, they test on ProcGen there, Brax there, completely different domain like Atari there, and it's just very hard to really see what works and what doesn't, and why it works and why it doesn't, and why something like on the fly hyperparameter adaptation is really getting a bit bigger now. But we don't really know how to do that at all. Like with on the fly, I mean doing something like a decaying exploration during the runtime, which is really what we want, right? And ideally, we would want that to be reactive to a degree, seeing, okay, now performance gets better, now we can really, lay off that a bit. But really, this is something that methods struggle to do in an informed way right now. So we compared a few things there. We compared a few PBT-style methods, which really rely on this large parallelization, running for an interval of time, and then interrupting training between 10 to 20 times, usually, overwriting the worst agents with the weights of the best ones, proposing a new configuration. And the ones we tried to do that with Bayesian optimization in the loop. We also tried random search, which has argued and has been shown in many dimensions to be more efficient than grid search. And then the last one we tried is DE hyperband, which is something that has been performing really well in just the hyperparameter optimization community for supervised learning. It's a combination of something that hyperband is a scheduler, so meaning it selects how long we run our agent for until we say, okay, this is the performance we're just going to use as an estimate. DE is an evolutionary strategy. So the first thing we found is that if we just try to use them instead of grid searches, we do fairly well with a smaller budget. So this says low budget and hand-tuned in HBO, this graph. What hand-tuned means is we looked at 2 papers. One is the IDAG paper, I don't know if you know it, which is looking at ProcGen and how to set up actor-critic architectures on ProcGen. And the other one is the Brax paper. And we took the hyperparameters from those, reran them, and compared their tuning budget that they state to what we use as a budget and what we have in performance. So what we show here is the performance of DEB is that. So that's the DE hyperband method we've known from algorithm configuration. That's pretty good. I think there's one environment, Plunder, where it's kind of fails compared to hand-tuned, but our budget was 12 times lower than that of the Brax paper, and I think it was like 20 times lower than that of the IDEC paper. So this is a significant reduction in cost that we have here, and overall performance stays comparable. So first insight is, while methods that tune RL and that exist, if they're RL specific or not, they can be much cheaper than what we see in the literature. We also looked at it a bit more in depth, though, to see where the issue came from, why we didn't see more of those, why we don't, see tons of papers like we see for supervised learning, having really intricate tuning strategies. And it turns out the whole thing is a bit more complicated than we thought. So basically, we have a darker and a lighter color here for each of the lines, right? We have something like the dark green and the light green. And on the right here is our baseline. This is the IVAC paper. This is the one we performed a bit worse on. And its grid search budget was 810 runs. So 810 different combinations of things. And we ran with 16 total runs and 64 total runs. And we can definitely see that some methods, as we've seen in the previous graph, perform really well at times. But if you look closely, oftentimes that is the darker one. The darker one is the tuning seed. So if we look at the performance on the setting, where exactly we tuned them. So we took 5 seeds and said we evaluate, we tune across those seeds and also evaluate on those seeds. And suddenly we see crazy performances. For example, this brown line here, that's PB2. So just Bayesian optimization plus PBT. And it's incredibly good. This is a score on this environment. It's just crazy. But then we look at what happens if we just change the seeds and nothing else for the same hyperparameters. That's a difference of about 8 times in performance. This is generally pretty bad, obviously. That's kind of a testament to how well this method tailors the hyperparameters it finds to the setting at hand, which for a dynamic method makes sense, I think, because you have this massive parallelism. And if there's one of these, in this case, 16 agents that manages to exploit the exact random state that we see in the beginning in its, for example, exploration and optimization, obviously we're going to get a massive boost in the beginning. And this is an environment that has a very smooth, dense learning curve. So we just start off very quickly. We can progress very quickly. So this is not surprising from the method point, but it's not what we want, right? It's neither what we want in practice. We don't want to spend compute on tuning something on an environment only to notice we can only use these 2, 3, 4, 5 seeds on it. And we also don't want to use this in comparisons with other papers. Like if I do this in my paper and someone, if you want to use that as a baseline, but by accident use like 2 seeds from this seed collection and 5 seeds from this seed collection, like your performance will be all over the place. It will be a bit confusing, and you'll probably also skew your performance comparisons to your own algorithms. And we found this is actually a major difficulty for all methods we tested. Like even random search does this. You would see, say, random search doesn't really is a method that doesn't really actively search for a bias in data like this. And still we see here that's half as much performance roundabout. I would say here a bit even less if we give it more time. And that's what we found is an incredible difficulty factor. And I'm not sure if this has been looked at in AutoRL systems that actually did things like, meta-learn whole algorithms. But I would be really interested to see if that doesn't persist on that level as well. So so that was kind of how we went out of this paper's exploration. We said, okay, let's set a template of how we think we should even tune our algorithms, how we should even touch hyperparameters there. We should probably go with generous configuration spaces because so many hyperparameters matter. Just say, okay, we have a relatively large search space because we've tried that as well and see that these algorithms can actually handle that. It doesn't really matter that much. And then we kind of do need to define tuning and testing settings that need to keep them separate. We need to make sure we set the different seeds, we set different environment variations, and we set a budget that we keep for same methods and baselines in the same way, because we are able to introduce massive amounts of performance bias here. And then we should compare the test setting, because in the end, that's what we care about, right? We care about what our method, any method, can generally do. But it's kind of not very satisfying, right? Mm-hmm.
Hey, Theresa. Just a quick question for now. When you're saying tuning over various seeds, this is actually something that we've been thinking about recently. And the approach that we've taken is, suppose your optimization algorithm suggests a set of hyperparameters. We roll out training over, like in our case, 3 seeds. You roll out training 3 times, and then we take the mean over the performance and allow the algorithm to optimize like that. Is this what you did as well, or is there a better way to like search over multiple seeds?
So there is a better way, I think, but that's what we did, because it's like the easy thing, right? And you also know which seeds you train on test on, which was part of the exploration there. In algorithm configuration, what is sometimes done is explicitly have optimizers that will also suggest seeds. So I know of one tool that's developed within my group that's called SMAC. And if you, under certain settings, it will have, it will suggest more seeds if the optimizer sees large variations in the data. So if the results from different seeds seem very different, you'll get more and different seeds to evaluate on. That's something I think that's a bit more studied in the algorithm configuration community and hasn't really been tried that much in RL so far. I'm also not sure, to be honest, like if that wouldn't end up with optimizing suggesting many, many validation seeds. That is a possibility with the current setup. Caveat.
I see. Thank you so much.
Yeah, but what I find a bit unsatisfying about this whole thing is that it's still, we don't really have an answer. We know that there's this problem that's kind of also inherent to RL, as we know, there's large discrepancies, and now we've seen that we can introduce even bigger biases to seeds if we tune hyperparameters on them. And even though we can do so fairly cheap, I think 16 full algorithm runs compared to 810, and still getting like in the area of performance a lot of cases, that's really cool, but it's still very manual in a way, right? We spend a lot of compute in it and it works, but that's not really where we want to go. So that's where I think we actually have an opportunity in research to go a bit further than this, to go what I call beyond classic HBO. And as classic HBO, I would say, is black box optimization. So, for example, using classic Bayesian optimization, also using things like evolutionary strategies, CMAES or DE, using single objective optimization, where you just get your reward, your evaluation reward, whatever you optimize on, right? And the unfortunate thing here, it's not very generalizable, right? You do that, and as we see, it doesn't even generalize to seeds in reinforcement learning. What we can instead do is we can look at meta-learned design decisions. We can also look at heuristics based on algorithm statistics. For example, I think there's been some studies on, more like workshop paper level studies on, can we adjust things like the learning rate or exploration if we just look at the development of the value function or Q values? And things like this, these would actually be transferable across domains, because hopefully we would learn something about the algorithms themselves, but not in a big picture way, as in we learned a full algorithm that is really specific to a domain, but we learned something general about an algorithm that we can hopefully use across many domains. And there's examples for this working, just not in RL. This is DAC, as we call it here, dynamic algorithm configuration, which does something very similar. Tries to do a hyperparameter optimization during the algorithm runtime, which I think for RL is also very, very important, and across multiple instances, so that we actually have something that can do this in a generalizable way. And there's been several successful applications, for example, in evolutionary algorithms. So this is a graph on step size adaptation for CMAES. And the interesting part is that blue line here, where we do need a while to actually learn anything. But then it's better than this, which is the next line up is the theoretical best hyperparameter value we could come up with in a static setting. And the light pink line that is actually down is actually the best per instance static solver. So this actually works really well. In the meta-learning design decisions, at first, of course, sounds very hard. This actually does very well in this domain. And the same goes for planning algorithms, where we can see a similar effect. I mean, there's an oracle here for the dynamic configuration, which is even lower, but it still can get better and does get better in practice than the static solvers, or the things that, do the black box optimization on single objectives. And the same also goes for supervised learning. So we've tried this for CNNs. These are some small CNNs. This is not like state-of-the-art image recognition or something, but at least on smaller domains as a proof of concept, this also definitely works for other learning algorithms. So I think we can totally bootstrap off of those domains and kind of go towards that in RL, HPO for RL. I really think that's kind of the next thing. This is more of a motivational call because I think that's going to be really relevant. I think it's going to actually be more relevant than learning bigger components for algorithms, since these bigger components so far have really shown to not be able to generalize well, because we really learn the whole thing on a set of domains. And here we can condition a bit more on the algorithm itself, I hope. We already have some meaningful baselines, and we know they have really glaring issues that we might not be able to fix, for example, the overfitting on the seats. And plus, if we can do this well, at least on the EA domain and DAC, there's been some really interesting also theoretical results, which I'm not optimistic enough to assume for empirical reinforcement learning, but we can still find some interesting insights into what learn schedules tell us, for example, about how learning rates should function in total on a policy gradient algorithm that I think will also help us build better algorithms. Plus, this is often also more interpretable than higher level meta learning. So after playing a bit with this black box algorithm configuration for RL, I've basically come away saying, yeah, it works, but I think the fix for it will actually be focusing more on meta learning for hyperparameters. But yeah, I'm really interested what you think about that topic.
So I'm not sure how many teams at the minute are directly using I guess meta-learned parameter optimization. One area that I'm really interested in is using this not just at the the algorithmic level, but at the system level. We've done work in the past where we've done large-scale distributed RL training, and we've had issues of trying to balance things like actors, learners, environment, workload, and all these things. And we spend as much time trying to tune the system parameters for convergence and throughput as we do the algorithmic parameters, which just adds more complexity to it. So I'm personally very excited for any sort of auto configuration that is looking at the problem at the system level, as opposed to at the, the individual component level. One thing I'd be interested to get insight on is there any evidence to show that continuous online hyperparameter tuning, where you are continuously changing the hyperparameters throughout training, does in fact perform better than, like a tabula rasa approach with an optimal configuration? Like if you tune it, if you do a training run, find your optimal configuration, and then use that from the start, is that able to get as good or better? Or is there evidence to show that the way to do it is continually tuning the parameters?
I'm just going to answer the question, Nima, or is that a comment on that as well?
No, go on. I have another question.
Yeah, that was just perfectly timed. Yeah, maybe for algorithm configuration on system levels first. Loads of algorithm configuration is still very focused on black box solving, even though transfer learning is becoming a bigger topic. So I think those you could use on a system level in theory, because you only need some sort of performance signal back. But obviously, I'm not sure how extensive it is to run it a lot. I think for that, it might be good to look into. I think there's some work on low-cost Bayesian optimization where you don't need many functional algorithms. That's probably a direction there. But yeah, as for the evidence, I think there's two pieces of evidence where I think they are. They point to that. I'm not. It's hard to say anything is proven, right? But there's two things. One is a paper, I think I mentioned it somewhere here, that a colleagues of mine wrote, that is about hyperparameter landscapes in reinforcement learning. And they obviously couldn't perfectly try to do loads of dynamic evaluations, but they found a scheme where they could afford many of them, and really found that the optimal hyperparameter values for example, learning rates on SAC, and I think one other algorithm, but I'm not sure if it was PPO now, really lie in different regions at different points in training. So I think that that's something. I think we've also empirically seen things like, for example, decaying exploration values working better in practice in some sense. Although you could, of course, argue that's maybe just because if you don't tune them well, the decaying might be a good fix for that. And the other thing is actually, okay, now somehow it slides. Don't want me to go back now. The other thing, what leads me to believe this is this. It's really this bar that we see here. And we see this in a few versions of population-based training. So we tuned more than once here. And we have a mean value here. And we saw that a few times, though, that sometimes these population-based methods just were incredibly good. I mean, this is the only time they were consistently incredibly good on the same environment. But we had a few runs there where we looked at them and said, this is a final performance that's just, out of this world in a way. And that really only happened on those. And now, again, this might not be a generalizable dynamic configuration. That's another question entirely. But I do think there's some evidence towards that. Absolutely.
Awesome. Thank you.
So I have another question. It's rather follow-up of Donald's question. I mean, I didn't see among the methods listed here using reinforcement learning for doing the control of it's a control problem, right? I mean, if it's really a dynamic thing, it might make sense to have a look at the history and then decide what's the next thing.
That's true. That's actually, we didn't do it here, but for these other two plots, that's exactly what we used. We haven't actually done that for RL in the inner loop yet. I really hope we can do that soon. I think at the point where we looked into these two domains, that was pre the, jacks becoming bigger. And so we thought it would always be computationally infeasible for us to have reinforcement learning as a target problem, because we didn't know how long we would actually have to train on this. And we also thought RL might actually be kind of hard, but especially with the efficient implementations we now have, thanks to something like jacks. I really hope that this is coming soon.
Thanks.
I suppose if we're good to open up for more questions, one on my side is like, from your work, have you seen any algorithms in particular that are easier to apply AutoRL and hyperparameter tuning to, or is there any that are more stable or easier to optimize than others?
Yeah, this is the point where I should have put in backup slides, I think. In that paper I talked about, in that called hyperparameters and reinforcement learning and how to tune them. And we also did something called not partial dependency plot, but we did plot hyperparameter regions against one another, basically seeing, okay, if the learning rate changed in this way in the configuration, did it in some way influence other hyperparameters, and how big the well-performing regions look like. So, and from looking at them, what we really definitely saw is that SAC is much harder to tune than both QQN and PPO. And PPO seemed really stable overall, had almost no interaction, I think no interaction at all, that we saw in the domains we looked at between different hyperparameters. The regions that performed well were nicely connected, no weird islands of, oh, this performs well, and then something at the other end of the landscape performs well. But yeah, SAC was a lot more challenging that way.
Yeah, it's funny. Just today, I was talking with some team members, and they made the same observation. That funny enough, SAC is supposed to be a robust algorithm, but we have had the most pain in trying to tune it compared to PPO.
Yeah, that's really interesting. I still don't quite know how that happened, but also that's something I heard afterwards as well. I talked to people after finding this, and they were also like, yeah, that's actually true. That's actually why I don't use SAC.
Yeah, Mohammed? I don't think we can hear you. I don't think the audio is coming through.
Okay, it's okay.
Yeah, no.
Good. So thank you for the presentation. I have just one question about which hyperparameters, how to predict. Is there a way to find how to predict which hyperparameters to optimize? Because as we see here for each experiment there is different hyperparameters to optimize. So is there any way to do this? Because as you said, yes, these are the gradient and the train. So these ones, but is there any other? Because we don't know for other experience. Thank you.
Yeah, this is a very, very good question. That's not only I don't know the answer to for reinforcement learning. I think the whole AutoML community doesn't know the answer to yet. That's a bit unfortunate. I think there's some work that's starting to come up, but I think most of those are just ideas of trying to change the configuration space once we've seen a few configurations. So once we've had the opportunity to try out a bit to say, okay, apparently this doesn't seem to make a difference. But as of right now, there's nothing that would be close to application ready, I think. But what I have to say, though, it seemed like the biggest difficulty, at least we found in trying out different ways of optimizing hyperparameters in RL, was really that performance estimation, that instability that we had in there. And we used pretty large search spaces. I think it was between 11 and 8 hyperparameters, and kept the ranges incredibly large. And that was fine. So my first intuition would probably be to just put everything in the search space and trust that modern, at least algorithm configuration methods actually work with that, because most of them do.
Thank you.
Yeah. So thank you for this nice and clear presentation. The question, so based on your experience, have you seen any correlation between certain types of environment and certain sensitivity to one hyperparameter? For instance, robotics application with large state space or image-based environment, or what, like any correlation between, if I have an environment, I could say, okay, because of this, I suspect that this set of hyperparameters is more important than the others.
Yeah, I mean, unfortunately, it kind of goes back to what I also said before. We really didn't. We tried a few environments for each domain that were quite similar, and then we tried different domains. And then it's, for me, it's at least hard to extrapolate from that. So, for example, I had a big surprise when I saw that, you know, clipping factors of like 0.8 worked the best for PPO on Walker environments and Brax. That was really strange to me, and to stay consistent across those environments. But I'm not sure if that was an artifact for the walking, if that's an artifact of robotics environments or something. I think for that we'd really need a few more studies, because right now I also the few interesting things we saw, I personally couldn't connect them back to anything of what's going on in the environment. For example, the batch size. As I said, there's this NURBS paper that now looked at batch sizes in exploration environments and really explains why they're really important. I saw that the batch size is apparently really important, but just from seeing that, I couldn't actually infer anything more general about them and why that could be the case. So I think this is more like these hyperparameter importance now, I think, are more like intros into what would be interesting to explore in a domain, and maybe to look into a bit more broadly. But at least me, I couldn't tell you much about actual, you know, general statements from them just yet.
Great. Yeah, thank you.
I guess one more question for me. So earlier in the talk, you were kind of highlighting the difficulty and challenge of RL, that the policy that you are learning is directly impacting the data you are updating to, and can cause this instability in your learning landscape. Is there any evidence to show that like offline methods or a hybrid of offline and online improve this and are maybe less susceptible to the divergence in seed or anything like that?
Unfortunately, not yet. I've looked for this, and I also thought, actually, for the AutoRL community, wouldn't offline methods actually be the better target? Because you don't have this this loop there, right? You can focus on one aspect, namely just learning the best model you can, given the data you have. And the work there really seems to focus a lot on how do you proxy performance? Like if you don't want to actually do online evaluation, how do you find a good proxy performance, right? But not much in the sense of even just applying current algorithm configuration methods in there. It's kind of baffling to me, but I think that's just because the field is still very much growing. I mean, yeah, I said the original PBT paper was 2017, but not a lot happened for a few years there, and I think it's only really been relatively recently that the topic has been picking up. But I do think that that would be a nice target domain in a way, even though obviously I think the usage of online RL is great. I think offline would be a good way of developing stable methods first.
Cool, thank you. Any other questions, guys? Maybe one last one from my side. What would be your advice on methods to use to start introducing AutoRL into an RL workload? That is, in your opinion, is the best starting point, the most robust, let's say.
Yeah, I at least in our comparison, DEB performed really well, but I'm not sure. I don't think that's something that's unique to DEB per se, but to the ingredients that are in there. So what's in DEB is a black box optimizer, in this case DE, and black box optimizer are very common in different packages for hyperparameter optimization. For example, BO is also a black box optimizer, and you can find that in stuff like Optuna. You can find that in other AutoML packages. And the other thing is the HB part, the hyperband part. That's a scheduler, and I think that really helps because I believe even in RL, you can just tell if a configuration is bad after some point. You don't need to run the whole run. That will cost you a lot of compute that's unnecessary. So having any sort of scheduler, and the keyword hyperband or successive halving, I think is in there as pretty well, and some sort of black box optimizer, because those seem to be the most stable right now, would work really well. So as I said, Optuna has that. We have that tool SMEG. DEB is out there as well. And there's just different implementations of those depending on how you run your workflows. I think I'd start with either of them because they are the static methods just seem to be more stable for now.
Okay, awesome. Thank you very much. Guys, last chance. Any questions before we finish up?
One final question from my side is it, especially for RL workloads, when you're like tuning over hyperparameters, do you think it's okay? So let's say I want to run an experiment that's going to run for very, very long at evaluation at the end of the day. Do you think it's sufficient to tune on a shorter experiment? So for example, let's say I'm going to run an evaluation for like 30 million time steps or something, to tune only up to like 10 or something like that.
Yeah, so that's an interesting question. We've not directly run into many problems doing that. That's in a way what Hyperband did in our experiment. So Hyperband like progressively just increased the experiment length, and I think in the end we only ran like maybe 2 full runs out of the 16, and the rest were kind of truncated. But there was, I think, 1 or 2 of the experiments, not the ones I've shown, but smaller ones, where we saw some weird aberrations. And we discussed it a lot, and we couldn't really prove it. But in the end, we thought what happened is that this cutting off of the runtime, and assuming this is the actual performance, ended up being a bit too greedy in a way. That, you know, we just didn't see the learning effect yet. So this can happen. I think it's a really good idea, but I think it's important to think about what's a realistic minimal runtime you need to see an effect. Yeah.
Great, thank you so much.
Okay, awesome. Listen, Theresa, thank you so much for the presentation. It was very insightful, and I think everyone got a lot out of it. Yeah, thank you for joining us, and yeah, hopefully we can stay in touch. And if there's any questions, I'm sure we can send them on, or vice versa.
Yeah, absolutely. Thanks for having me.
Awesome. Thank you very much. I will finish the recording now.